So then let's please welcome Dr. Ching-Hao Chang from National Cheng Kung University in Taiwan. And he's going to tell us about carrier-driven coupling in ferromagnetic oxide heterostructures. So yeah, please.
Thank you for the introduction, and thanks for organizers for inviting me to be here to share my studies. So my talk is carrier-driven coupling in ferromagnetic oxide heterostructure. Basically, this work is collaborates with a lot of Indian scientists, so it's nice to be here to show this study. I'm Ching-Hao Chang from National Cheng Kung University in Taiwan, and this work is collaborates with Ganesh, who is also here, Professor Ganesh, and Dr. Suja Das, and also Sanjit Kumar, and we also have some ab initio calculation from another group in Taiwan. So this is my outline. So I would like to talk about some. So I focus on the spintronics and the magnetic properties. So we focus on such kind of system, which is ferromagnetic oxide heterostructure, and we find in such kind of heterostructure, the magnetic coupling and also other magnetic property like the magnetic anisotropy are strongly affected by the spin polarized carrier in such kind of system. And the goal of our studies want to find new materials for developing spintronics. So let's start from the heterostructure of the SRO and the LAMO, strong leucine oxide, and this kind of material. So this kind of material, it was observed to have anti-ferromagnetic coupling in this superlattice. That means when we have this kind of superlattice, and we decrease as we decrease the temperature will firstly reach the TC of LAMO. So the LAMO will prefer to align along the external field. And then when the TC is further go down to below the strongly leucine oxides, then the strongly leucine oxide also prefer to have magnetization. But the direction of the magnetization is anti-parallel to the LAMO. So we can also see this feature from the NT curve. I mean, if we decrease the temperature and then measure the magnetic moments, we firstly find an increase of the magnetic moments due to the alignment of this LAMO magnetization. And then the magnetic moment become decreased due to when the temperature is below the TC of SRO. So this is due to the anti-alignment of these SRO layers. So this is a quite general feature. Even we change the width of the SRO, we also see this feature. So in this system, these two layers, these two materials are coupled, anti-ferromagnetic, and they also show some small magnetic anisotropy if we switch the field, external field from parallel to perpendicular to this superlattice. We can also measure some signal. But basically, this system have anti-ferromagnetic coupling. And we can also see this feature from the NH curve. In the NH curve, when the TC is above the temperature of LSNO, it's just like a conventional NH curve. But when the TC is below the Curie temperature of the SRO, then we can see these two loops due to the interplay between the external magnetic field and the anti-ferromagnetic coupling. In a very strong magnetic field, applied magnetic field, both materials are all aligned to the same direction. But then the magnetic moment switch anti-ferromagnetic due to the internal anti-ferromagnetic coupling. And then again go back to the same direction where the external field is strong enough. So this system, experimentalists already confirmed they have anti-ferromagnetic coupling. So to understand this feature, we first come back to understand the nature of this material, how the magnetization occurs in such kind of material. So we firstly see the LAMO material. This A can be Ca or Sr. So in this kind of material, the Eg and the T2G are filled. But because we have some doping, so the EG is only partially filled. So the carrier can move in around this EG orbital. So the carriers basically have the same spin polarization as with the net moment. So the carrier is parallel to the net moment, but the magnetization in such kind of material is mediated by the carrier. So it was the same. It is also the same for the SRRU03, but the situation is slightly different because in this kind of material, the carrier only fill in T2G band, and the carrier is anti-parallel to the local moments, to these three local moments. So this carrier, this magnetic carrier mediates the net moment. So in this system, in both systems, the magnetization are both mediated by the spin polarized carrier. So we think the spin polarized carriers must play a very important role in this kind of heterostructure. But if we go back to see some pioneer studies, there are already some theoretical understanding of this system. But they use ab initio calculation to study this system microscopically. But finally, they come out with a model that they assume there's no rule of the carrier. There's just coupling between the moments of different sides. And these two materials just couple with each other at the interface. So we are not so satisfied about this model because they only consider the local interaction and then there is no rule of the carriers, which is very important in both materials. So that's our starting point. So we are thinking that can we construct another model based on totally on the carrier to understand the magnetic coupling in such kind of system. So we have a picture that's we think in this system when the temperature is below the TC of the LAMO, it is naturally the moments of the LAMO layers are aligned to the applied magnetic field. But at this time, the SRO carriers are also spin polarized due to these moments in the LAMO layers. As we said, it's in SRO, the local moments and the carriers spin are coupled with each other. So if the temperature is further low down than the TC of the SRO, then this spin polarized should be polarized the moments to decide the direction of the SRO layers. So this is our picture. That's our physical picture. That's when the TC is between the LAMO and the SRO, we know the LAMO moments are aligned to the external magnetic field. So at this time, the carrier, this is just a simple quantum picture. But if we are the carrier inside the SRO, we will see the spin-dependent reflection due to this LAMO layer. So for the spin-down carrier, we consider an extreme case that the spin-down carrier are totally reflected by the LAMO layer because the spin are anti-parallel to the LAMO layer. But in other case, in other spin, the spin up can propagate around all the system. So the carrier for these two kind of carrier have quite different potentials. So we can understand that the density of state must be quite different in these two for these two kind of spin carrier. For the spin up, it's just like a normal free electron and have a parabolic band. But for spin down, as we say, the moments in LAMO strongly spin-dependent reflect this carrier. So the spin-down carrier can form the quantum wheel resonance and form these quantum wheel state labels. So then we can, at the end, we can find the spin-up carrier will always have higher polarization, higher density of state rather than spin-down carrier due to the spin-down carrier have this quantum wheel resonance. So if this happens when we continue go down the TC to below the TC of SRO, the moments in SRO is also polarized by the local moment in SRO can also polarized by this polarization due to the spin-dependent potential. So this is our picture to understand this system. And then from this picture, we can also understand why the system always select anti-ferromagnetic coupling. This is due to the nature of the carriers in this in this superlattice. So with this picture, we start to collaborate with Professor Sanjit Kumar to develop a microscopic model to really study this system. So we build a model based on the carrier. So we have two kinds of carrier and we have two kinds of material. So the carrier, in our new Hamiltonian, the carrier can couple with the local moments, and the carrier also have the kinetic energy to move around. So in this model, we can include the rule of the local spin and also the itinerant carriers, and to see what happens in this system due to these itinerant carriers. So we can plug in some model parameter in this system. So, so here are 4 pictures that we change the strength of the magnetic coupling between carrier and the local moments. And we plug in this parameter, and we see that if the coupling between the Lucinian and the carriers, when the coupling is strong enough, we indeed see this NH curve, NT curve, like as shown in the experiments. So from this model, we can indeed expand the behavior of the NT curve in the measurements. Besides, we can also use this method to use this model to calculate the NH curve, and we indeed see two loops due to the anti-ferromagnetic coupling of these two layers. So this is also consistent with the experimental measurement. So this NN are the different thickness of the SRO and the LAMO. So here we can provide another picture based on the carrier-driven magnetic coupling to expand for all the features in this system, including the anti-ferromagnetic coupling and also the NT curve and also the NH curve. But this is just a model, so we are thinking furthermore, that's not only experimentation, can we predict something new in this system based on our model? So in our previous picture, we focus on expand the anti-ferromagnetic coupling in the LSNO and the SRO system. And we think what will happen if we change this system to bilayer. So this is quite different. For bilayer, if we have this LAMO SRO bilayer, so when the temperature is below the TC of LAMO, this bilayer, this LAMO layer basically provide a quantum wave for the spin polarized carrier in the SRO. So the carrier of different spin see the different width of the quantum wave. So if this happens, then we can see both carrier can form quantum wave resonance, and the quantum wave resonance will. So this is we select a typical width of SRO, and we can plot the density of state. So we can see that both the carrier can form quantum wave state and to form this step-like density of state. So we can cut a Fermi label. If we fix the Fermi label but change the number of the widths, we can see the spin polarization is changed with the number of the widths. Sometimes the spin down carrier have more density, and sometimes spin up carrier are more. So in this system, we can predict in a bilateral system, there maybe have oscillatory magnetic coupling in such kind of system. That means if we change the width in the bilateral system, the magnetic coupling is not always anti-ferromagnetic coupling. It will switch between ferromagnetic and anti-ferromagnetic. So we are still work with experimentalists to realize our prediction. But this part is already confirmed by my collaborator who doing the ab initio calculation. So yeah, and so this is my summary in this part. We address the anti-ferromagnetic coupling in LSNO SRO superlattice by the carrier, and we expand the NT curve and NH curve in this system. And we further predict there may be a oscillatory magnetic coupling in the LAMO SRO. And if experimentalists can observe the switch between anti-ferromagnetic coupling and the ferromagnetic coupling in this system with different widths, then this can prove our picture is correct in this system. Besides the heterostructure with two magnetic material, we also consider other possibilities, like we couple the SRO with the similar system, but without the magnetization. So we also check what will happen in this kind of system. So in this kind of system, so this SRRU03 and the CARU03, their electronic structure are quite similar, but only in SRRU03 have magnetization, have spin polarized carrier. So we also test what happens if we combine this material together. Can we introduce the spin polarization in this system and then drive the magnetization in this system? The answer is yes. So this is our model. We check what will happen in this system. We calculate the spin-dependent scattering due to a SRO layer, and we check the carrier distribution around the SRO carrier. So we can see in the CRO carrier, we see this Friedel-like oscillation. This is just like a Friedel-like oscillation due to a giant spin at here. So we can indeed induce the spin polarization oscillation in the CRO carrier in the CRO layer. And if the temperature is low enough, this spin polarization oscillation may introduce the magnetization in CRO layer. So if the temperature is low enough, we expect we can see also the magnetization due to this spin polarized but also oscillatory carrier. Besides the magnetization, if we check this structure, this is like a SRO layer with anti-ferromagnetic layer. So there may be also the exchange bias can measure in this SRO layer. And this is indeed measured by our experiment collaborate. They indeed measure a small magnetic moment in CRO layer in a very low temperature due to the SRO layer. And they also measure exchange bias in this kind of heterostructure. So if you are interested, you can also check this, our new paper, just put on the archive. Also, do I still have time? Okay. So is any problem for this part, or I just continue move on? Okay. In the first part, from our model, we found that the spin polarized carrier, also the quantum resonance is quite important for this kind of heterostructure based on ferromagnetic oxide. And recently we also studied further about this system. We check, can we also, if it's not a heterostructure, it's just a single layer, can this quantum wave resonance, also this spin polarized, we want to check if this carrier also impact other magnetic property. So this is an example. We found that the easiest, the magnetic and anisotropy in the SRO layer is also related to the spin polarized carrier. So let's talk about what is the magnetic and anisotropy energy. If we have a magnetism field, so if we consider the moments or the magnetization direction of the moments, we have two kinds of choice. One, the moment can perpendicular to the surface of the same thing. And another choice is the moment can align the same thing. So the difference of the total energy between these two systems is the magnetic and anisotropy energy. So this is already have been studied for quite a long time, and people already know that the spin orbital coupling dominates this magnetic and anisotropy energy. But this is very important field quantity because in many magnetic-based devices, in many devices like memory device, this magnetic and control or tighter or tune this magnetic and anisotropy is very important to develop this device. but it's very hard to understand how to control this magnetic anisotropy, because in real material, the band structure is quite complex, and it's hard to analyze how to control this magnetic anisotropy. But as we have said, that SRO has quite good feature because the spin are polarized, are highly polarized near the Fermi level, and if this SRO make into a same thing, we have a quantum well state that's spin polarized. So in SRO, it's quite clear that we can only focus on one kind of carrier to check how to control the magnetic anisotropy. So this is a band structure of the SRO, of a single SRO layer of H unit cell. And we can see this quantum well state structure due to the confinement along the z direction. And also in the density of state, we can see this step-like feature due to this quantum well state. So we can calculate, we can put in the spin orbital coupling Hamiltonian to see the difference of total energy and also band structure in these two systems. So if there are no spin orbital coupling for minority carrier, they have a degeneracy in the gamma points. But if we turn on the spin orbital coupling, there's a large energy gap can open by this spin orbital coupling turn, and this will largely change the density of state near the Fermi surface. So, but in another case, when the moment is in plane, then this perturbation is not so. It's go to second order, and the gap is quite small. So use this way, we can control the density of state in the Fermi level by switch the direction of the magnetization. And this also change largely the energy of this system. Because in this system, for the moment parallel to the z direction, the density state is quite low comparing to the moment at the in-plane direction. Because this large gap can naturally reduce the density of state to reduce the total energy. So in this system, we can find they are quite consistent between the quantum well resonance. This is the spectrum of quantum well resonance. When we increase the layer of SRO, we can see quantum well state will pass the energy level, pass the Fermi level periodically, and this always refer to the maxima in the magnetic anisotropy energy. So I think this is the first system that can well control the magnetic anisotropy energy by the quantum well resonance. So we can also even do further. We can, as we said, this large magnetic anisotropy is due to there's a large gap, energy gap when the moment is along the z direction. So we can also shift the position of the energy level by put or decrease carriers in this system. So we can change the direction of the moment from parallel to the z direction to the in-plane at the z direction by just shift the Fermi level by increase more hole in this system. So this also indicates that in this system, one can tune the EZSs of SRO by electric way, like put more carrier or apply a gate voltage. So this indicates this system is quite good to design the memory device that can control electrically. So this is my summary in this part. We find it. So in the first part, we find the quantum well resonance and also the spin polarized carrier can mediate the magnetic coupling. And in this part, we find this carrier can do more to control even the EZSs in a single SRO layer. And we also find in this system, this is very possible to control the EZS by just apply the gate voltage. So finally, I would like to thank for all my collaborators. Ganesh is here, and also Chang, he's working on realize our prediction in experiments. And we also have collaborated from ab initio calculation. And yeah, and thank you for the listening. Yeah.
So we are now open for questions, comments.
So is it possible to generate some other non-collinear magnetic states, such as, for instance, Skerman lattice? If you can, Skerman lattice.
Yeah, Skerman.
Yes, Skerman lattice.
Yeah, that's also we are interested in not only tuning the magnetic anisotropy, but also to see what the DN interaction can. Yeah, this is also our direction, but we are not sure now. But we are quite interested in this direction. Yeah, you mean how this spin polarized carrier or how this?
You can use, for instance, imagine you make the heterostructure has some Rossby spin orbit coupling, so then effectively can generate RKKY, like which contain a during schema real interaction term that may generate Skerman lattice.
Yeah, we indeed work on this direction now, but yeah, you mean we put like an interface and the 2C, can we have some, can we introduce the Skerman by this spin polarized carrier? Or?
I'm just making a comment. If you if you can engineer in such a way, you can introduce a Rossby spin orbit coupling to the carrier, and then the carrier can induce effective RKKY interaction that contains during schema real interactions that may eventually lead to a Skerman lattice.
Yeah, thank you. Yeah.
Yeah.
Switch it on.
You are showing the experimental data of LAMO and SRO interface. First part of the talk. So there the MH hysteresis looks like showing that there is a phase separation in this interface. That means like you are showing that there is a anti-ferromagnetic coupling. Right, you are telling there is an anti-ferromagnetic coupling between the two layers, right?
Yeah.
But the thing is, like there are many bulk materials showing this type of hysteresis loops. That they are reporting that there is a there is a S-shape hysteresis curve. There are many bulk materials are showing that there are reports on the bulk materials. They are showing that there is a phase separation of antiferromagnetic and ferromagnetic. So like here, like this manganese and oxygen, like there is a combination of manganese oxide. There is antiferromagnetic material it may form, right? So is like whatever you are saying that what is a statement like a coupling, antiferromagnetic coupling between the two layers is something like I am suspecting that is due to the ferromagnetic and antiferromagnetic phases giving this type of structure, hysteresis loops.
You mean maybe there are some phase in their material. You mean this is may not due to the interlayer coupling, and then maybe due to there are some phase in the material? Or?
So I'm not able to hear. No, I am not able to hear your voice.
Oh, you mean? Okay. Okay. So. Can you say again your problem? You mean?
No, this there are two hysteresis loops, right?
Yeah.
Like whatever showing that S-shape hysteresis loop, So there are many bulk materials
I agree.
showing that there is a phase separation between the ferromagnetic and antiferromagnetic. Okay, so that type of behavior is showing this type of curves.
I know.
So like you are saying that there is antiferromagnetic coupling between the two lattices, two layers. Right.
Yeah, I agree that there would be another possible to lead to this to NH curve in this system. So that's why we want to find more evidence to go this bilayer system to check if this is correct or not. So I understand in this oxide material, in this ferromagnetic oxide material, sometimes even in SRO itself can show this curve. I know that. So yeah, I understand. Yeah. So we only give an experimentation in this, but we not totally confirm this is due to carrier. Yeah. So I agree with you about this point. So that's why we need to study more detailed in this system. Yeah.